So in this particular video, we will look at the motion of a mass that's attached to a massless spring with spring constant K while sliding on a frictionless surface. So in this particular case, the spring is given an initial impulse. So it's given an initial velocity, okay, and the spring mass system starts to vibrate. So we want to find out how the extension of the spring or the compression of the spring changes with time. So initially the compression or extension of the spring is 0, and we fix the coordinate system at the equilibrium where uh, at the equilibrium point when there is at which there is neither any compression nor any expansion of the spring. So here, since the mass is sliding on a frictionless surface, the change in energy of the system is 0, okay, at any point in time. So if we write Ke here equals half kx square, that's the potential energy of the spring, plus half mv square, that's the kinetic energy of the mass. So we can see here that dE or dt needs to be 0. Okay, so if we carry out the computations, we will see that k times x times dx or dt plus m times v times dv or dt is 0. Right? So let's rearrange the term some more. So m times v dv or dt equals minus kx dx or dt. Right? So rearranging this a little bit more by dividing by dx or dt on both sides, we get mv times dv or dt divided by dx or dt equals minus kx, right? And now dv or dt divided by dx or dt can be written as this. So it is dv or dx, right? So here m times v times dv or dx equals minus kx, okay? And m times, or let's say v times dv or dx, okay, is dx or dt times dv or dx. The dx's cancels out, and this is dv or dt. This is the acceleration of the system. So essentially here m times a is equals minus kx, and this is an expression of the Hooke's law. So we know that the equation is consistent with Hooke's law, but nevertheless let's continue. So rearranging terms a little bit more, v dv equals minus k divided by m times x dx, right? And then we integrate and we add a constant term. When we do that, we get v square divided by 2 equals minus kx square divided by m divided by 2 plus constant. So when x equals 0, we have the initial condition that v equals v0. Therefore, constant equals v0 square divided by 2. Okay. So here we get the expression v square equals minus k over m x square plus v0 square, right? And let's call this as omega, and we will see why in a bit, okay? Or to simplify this a little bit more, okay, let's take out the square sign from the left and write this, put a square root sign on the right, and we know that this is nothing but dx or dt. So what we do here is that we again rearrange the terms, and we get dx divided by v0 square minus omega square x square, square root of that, equals dt. And what we do is that we take out the omega square um, from near the x square, and so we will get something like this: dx divided by v0 square divided by omega square minus x square equals omega dt. Okay, and we add a constant term which we'll call as phi. Okay. So now, so we make this transformation. Okay, x equals v0 divided by omega cosine theta, or let's, the easier thing to do is sine theta. Okay, so essentially the left hand side becomes v0 by omega cosine theta d theta divided by v0 by omega cosine theta. Okay, and that's nothing but integral of d theta, and that's theta, right? So now, so what we can write here is that is theta equals sine inverse x divided by v0 by omega. Okay, so what happens here is that we can write this expression here is that sine inverse x divided by v0 by omega equals omega t plus some constant, or we can write x here equals v0 divided by omega. Let me write this a little bit better. Omega sine omega t plus phi. Okay, so what we can see here is that we could have even substituted cosine omega, okay, cosine theta instead of sine theta. So if we write this expression here as generally as a times sine omega t plus phi, okay, we can also write x as b times cosine of omega t plus phi. So more generally, x can be written as a times sine omega t plus phi plus cosine b plus b times cosine omega t plus phi. Okay, so there are two trig terms possible, and depending on the initial conditions and the boundary conditions, we can solve this equation this way. Okay, so for now, if we omit that any consideration of these mixed terms, so let's just think of x equals a times sine omega t plus phi. So the phi is called the initial phase. Okay, and omega is the angular velocity. Okay, or the angular frequency rather. Okay. So we can write this as omega equals 2 pi divided by t. Okay, so therefore we can, where t is basically called the time period, so x equals a times sine 2 pi t divided by capital T plus phi, and here this is called the amplitude. Okay, this is the maximum possible value of x. Okay, so the maximum possible compression or the maximum possible extension of the spring. Okay, t is the little t is the time, and the capital T is the time period. Okay, so this is the time required for the spring to complete one full cycle of vibration. Okay, so here we see that how simple harmonic motion equations can be created using energy conservation. So we first started with a statement for conservation of energy of energy, and wrote an energy conservation equation, and from that we came up with a an equation for motion of the system, right? And we use some mathematics to derive the velocity, right? The velocity of the system, right? derive the velocity of the system, and then use some more mathematics to find the, the, the position of the mass or the extension of the spring as a function of time. Okay, so let's do the same for uh, a pendulum system. Okay, so we know that if there is a pendulum that's hanging from a ceiling, right? It's hanging from a ceiling, and let's say it has made, right now the current position of the pendulum is such that so the string here makes an angle of theta with respect to uh, the vertical, and let us say the length of the pendulum string is capital L, right? So in this particular case, what we would see is that if you were to take this pendulum, and let's say it was here to begin with, and you were to give it a nudge, then this pendulum would go to this position, come back, and keep going till it would go to the other extreme, stop there, and then continue the motion that it had before. Okay, so that's what would happen. So the question is, can we rewrite the motion, as a simple harmonic motion? And the answer is yes, we absolutely can. So here, the the weight of the pendulum bob of mass m, okay, acts vertically downwards, and so if you look at resolving the weight in two directions, one perpendicular to the length of the string, okay, and one parallel to the length of the string, so you see that the component that's perpendicular to the length of the string is mg sine theta, okay, and here this is the angle theta, so this component is mg cosine theta, and the other component is mg sine theta. And so you can think of the restoring force, okay, restoring force equals mg sine theta, right? Mg sine theta. So corresponding to that, there is a torque, okay. So the torque here is mg sine theta times L, okay, where L is the length of the string. So now, we know that in this particular case, torque equals I alpha, okay, or I alpha in this particular case, okay, equals uh, the torque. But since the torque is a restoring force, corresponds to a restoring force, we would put a minus sign in here, and we would call this minus mgl times sine theta. So alpha here becomes minus mgl divided by I times sine theta, where I is the moment of inertia. Okay, moment of inertia. So now the alpha here can be written as d2 theta divided by dt square, okay, equals alpha. So we can write here is that d2 theta divided by dt square equals minus mgl divided by I times sine theta, right? And so what happens here is that when theta is very small, then sine theta is approximately equal to theta, okay. So d2 theta or dt square equals minus mgl divided by I times sine theta, or since we want to replace sine theta by theta, when theta is very small, that's what we come up with. And what we saw here, so let's compare that to the equation d2x divided by dt square equals minus k divided by m times x, right? So both these equations have the same structure. So for the bottom equation, omega equals square root of k over m, okay, and in the top equation, omega equals mgl divided by I, and we take the square root of that. So the equations are very similar. They have an identical form. Okay, and that's how we can find out the time period, you know, of the pendulum and so on and so forth. Okay, so but I wanted to show here how to derive these equations of motion. Okay, knowing the the energy conservation principles. Okay, and in the second part, we used an analogy, right? We found the restoring force, and we equated that to the we have a restoring force. We find the torque from that, and we equate that to the formal definition of the force, that's I alpha, of torque, that's I alpha. And when theta is small, okay, sine theta is essentially set to theta, and we get a form that's identical, okay, to the equation of motion for a mass attached to a spring. So I hope this will help you understand the mathematical underpinnings, okay, of the equations of simple harmonic motion. In a future video, we'll try to solve some problems related to these equations, and we'll go into depth on uh, how the amplitude and the angular acceleration or angular frequency and the time period can be derived, okay, from the various parameters given in the problem. Okay, thank you.